Hi, today we're in lesson 1, section 2, about relations and functions. And today we want to review a little bit about what you know about functions. Our objectives, as you can see, are determining whether or not a relation is a function, using function notation, and identifying the domain and range of a function. So to begin, we want to obviously talk a little bit about vocabulary. Folks, a relation is simply a set of ordered pairs. That's no more, set of ordered pairs, that is no more than a list of what we would traditionally call XY values. So I'm going to do that here, XY. The domain of a relation is the input value. Some people call it the independent value. Most commonly, most often, the x's, what goes into a function. The range is the output value, or dependent value, since the value of the range depends on what x is put into it, what domain element goes into it. For us, that's normally the y values. A function is simply a special type of relation. It is a relation where each member of the domain is paired with exactly one member of the range. A relation where each element or each item in the domain is paired with exactly one element in the range. Paired with exactly one item in the range. Good. All right, there are several ways that you can show relations, and one of them is just that list of ordered pairs. So by list. We often see relations shown in tables. If you can make a table out of something, you can make a graph out of it in the coordinate plane. So a third way of showing relations are graphs. And fourth is what's called a mapping. And a mapping is simply a visual that shows you how each input matches with its output. We'll see some examples of those coming right here. The very first one that we're looking at here is a mapping. Again, that's just a visual way of deciding which range element goes with which domain element. And the question for us is this relation a function? To be a function, each element in the domain must be paired with exactly one element in the range. And so I'm looking at this. -1 goes with 6 and 6 only. 3 goes with 8 and 8 only. 0 goes with 8 and 8 only. 2 goes with 6 and 6 only. Folks, this is a function since each element in the domain is mapped to exactly one element in the range. It doesn't matter that two domain elements have the same range values. What matters is if there's an x element, a domain element, it can only go to one range element, and that is what's happening in this picture. In this one, we have a circle. And I would submit to you that this is not a function. And the reason it's not is that there are many x's, x of 2 for example. When x is 2, there are 2 range elements or 2 y's associated with that. That is not a function. Okay? X equals 2 goes with more than one y. And that's not allowed in the world of functions. Now I'm looking at this set of table values that we're looking at. The domain, the x's, are -5, 3, -1, 1, and 3. All of those are different x's, and it looks like each x is matched with one element in the range in the y set. This is a function. In fact, this guy, this parabola, what do you think? Function or not? Is it possible to draw a vertical line that hits that U in more than one spot? I don't think so. Remember, folks, from your algebra, the vertical line test, this one passes the vertical line test. And what that tells you is that each x value, wherever you draw vertical, you only hit it one time, passes the vertical line test, so yes, that's a function. Now we've got a little activity for you to do here. We want you to select, it says some y values that will make a function. So in the y column, we want to match numbers up with these input numbers so that we get a function. And I'll tell you, as I'm looking at it, there are some x's that are repeated. And here's the deal. If we have repeated x, it always has to be with the same y number. So if I want this to be a function, and say -5 in the x is matched with 0 in the y, then this -5 in x must also be matched with a 0 in the y. And if I make this one go with 6, then that -3 has to go with 6, and I don't care what we do with this one, I'll make it 2. This is a function because each element in the input is matched with only one element in the output. If we want now, on the bottom or the next row in the table, select y1 values that will not make it a function. Boy, as soon as you have -5 matched with 0 here and matched with 10 here, that's not a function anymore because that one element in the domain is going with two different y's, and functions do not allow their x's to two-time on the y's. Okay? They have to stick and be faithful to only one y. So if this was 2 and say this was 8, we'd be in the same situation. So there's a list of y values or y1 values that would not make a function with this domain set. All right. What we're asked to do here is to solve each of these equation statements for y to determine if we have a function. So if I want to solve for y, I need to subtract 2x from both sides, and I would be looking at something like this. Y equals -2x plus 6. Now I would ask you to think about this. No matter what number I put in for x, say I put in 10, that is going to give me a specific y out. In fact, you can figure out what that y would be. If x were 10, then y would be -20 plus 6, -14. The x of 10 only goes with that one y. This is a function. In fact, folks, all lines are functions. Okay, they must be, because for every x that you put in, exactly one y would be output. I lied. No matter what number we say, if it's an x equals line, so I'm going to put a c for constant, that does not make a function, because if you think about that, if this is the point where x is c, it's also c on all of these points, so there are many, many, many y's that go with that x of c. Not a function. This is the exception. Every other line that you can talk about is a function except for this type of line, a vertical line. On this one, I can see the squares. That's not going to make a big difference in the way we solve. We still want to get y by itself. So we subtract off the x squared and we end up with y squared equals, we subtract x squared from both sides, so y squared equals 9 minus x squared. And take the square root on both sides, so y would equal the positive or negative square root, since there are two values that will create that y, a 9 minus x squared. And as soon as you think to yourself, this is going to, if I put an x of 1 in here, say, I would have the positive or negative square root of 9 minus 1, 8. That's two values. One x produces two y's. This is not a function. In fact, when you see an equation that has both x squared and y squared, that's the equation of a circle. And no circle can be a function. All right, since we are talking functions today, and since function has a very specific definition, if we have a function that's defined by some equation and the writer did not specify a domain, then you have to check to make sure that no x value will, I'm going to start a sentence there, no x value will, and there are two things to look for, create a negative under the radical, so create a negative or, a negative number, negative value under a radical, actually an even indexed radical, like a fourth root or a sixth root or a square root. Okay? Can't have a negative value under an even radical. And you also you can't have x values that will create 0 in the denominator of a fraction. Those are the two things that we have to look out for. If there are x values that do these things, we simply have to exclude them from the domain. In order to be a function, you can't include in the domain an x that will do this, create a negative under the radical or a 0 in the denominator. So if I'm asked to list the domain for this function, I have to think this has got the radical, obviously, a square root, so we said even radicals, and this one is one. We can't put in any x that would create something negative in there. So I would ask you to think about this. A good way to test, is it possible for me to put positive numbers in for x? And I'm going to check 1. So if I use x of 1, I get the square root of 1 plus 1, which is the square root of 2, and that is allowable. Right? That's not 0 under there, or it's not negative. What if I put in 0? 0 plus 1 is 1. The square root of 1 is 1. That's still okay. What if I put in negative 1? Well, the square root of negative 1 plus 1, the square root of 0 is 0. So that's all right too. But as soon as I get under negative 1, then I have an issue. Even if I said negative 1.11111, when I do the addition here, I'm going to have a negative value, not allowed. So the domain in this set is all x such that, remember that notation, x has to be greater than or equal to negative 1. Okay, that's the domain for that guy, D for domain. Over here we have a fraction, so we've got to consider excluding values that would make 0 in the denominator of that fraction. It might help us to get that factored a little bit, because I see we can take an x out of both terms there. That would be x minus 4, what's left over. So what are the two values that must be excluded here? You can't have an x of 0. You can't have an x of 4. So if we were to list the domain of this, all x such that x is not 0 and x is not not 4. All right, let's continue on today. Function notation. I hope that we can just make it clear right from the very start that when you see f of x, that is standing for y. Right? It's just another way to say, okay, this is going to be the output. X is the input, f of x is what you get out of it, or y is what you get out of it. When we see this f negative 3, that means in this function, not here, but here, we substitute in a negative 3 wherever we see an x. So f at negative 3 would equal negative 3 cubed plus 4 times negative 3 minus 6. And doing the math real quickly, 3 times 3, 9 times 3, 27. We're negative 27. And 4 times negative 3, negative 12. And minus 6, this is all negative. Look at that. 27, 39, negative 45. Okay? If we evaluate f at 2, this might be a good place for you to stop the video and see if you get the same thing that I do when we replace x with 2. F of 2 would be 2 cubed plus 4 times 2 minus 6, and that is 8 plus 8 minus 6, and I'm looking at a 10 right there. Is that what you got? I bet it is. All right, we're asked next to graph some functions and using a very specific domain. So even though the function rules look linear, we are not going after every input value here. We're only looking for those functions at these values for x, negative 3, negative 2, etc., up to 3. So if I am looking at the f function, and I'm going to graph that one in red, when I put negative 3 in there, I get negative 6. So negative 3, negative 6, right there. When I put negative 2 into this rule, negative 2 times 2 is negative 4. So negative 2, negative 4. When I put negative 1 and multiply it by 2, I get negative 2. 0 as an input gives me 0 as an output, and etc. 2 times 1 is 2. Put in 2, get 4. Put in 3, get 6. Now, I'm going to say, since we were graphing only over this specified domain, this is the graph. Normally, we'd connect those with a line, but this says, nope, just tell us what you get at the integer places. Now let's do the same thing for this other function, 2x minus 3. So now we're going to put in the x and then we're going to subtract 3. So 2 times negative 3 is negative 6, and negative 6 minus 3 is negative 9. When we put in negative 3, we got negative 9. So down here. And some of you are going to say, well, real quickly, boy, if we knew these f of x ones, all we got to do is subtract 3 away from them. And that is absolutely right. 2 times negative 2 is negative 4, and negative 4 minus 3 is negative 7. So we're talking right there. We put negative 1 in. We get negative 2 minus 3. That's negative 5 right there. At 0, we're going to get negative 3. At 1, 2 times 1 is 2, and 2 minus 3 is negative 1. So right here. At 2, 2 times 2 is 4. 4 minus 3 is 1. And at 3, 6 minus 3 is 3. Very good, and we've graphed those relations, the sets of ordered pairs that are f of x and g of x. And just for my peace of mind, what can you tell me about the graph of g of x, that's my blue, as related to f of x, which is my red? Well, they're always 3 units apart. You can tell that from the rule, but that creates parallel graphs. The graphs are parallel. Or you might think to yourself, g of x is 3 units lower than f of x. And perhaps you would find other ways to describe them, but those are the 2 things that I see most quickly. We reminded you of the vertical line test just a moment ago. Now we want to use that vertical line test to determine whether each of these graphs is a function, and then we are to find the domain and range of the ones that are functions. So I would ask you to think this: parabola. Is there any line for a vertical line that you can draw that will hit this in more than one spot? This one hits in one spot. This one hits in one spot. This one hits in one spot. In fact, there is no line, no vertical line that you can draw that will ever hit that parabola more than once. So this is a function, and its domain, let's write it in interval notation. That is, the domain of this are all x's as they go from negative infinity to infinity. That means any real number is okay. The range on this one, well, if you look at it, you'll see that the very lowest that it goes is negative 4. So the range on that first parabola has, actually we can put a bracket here because negative 4 is included in the range, and it goes through infinity. That is, it will grow increasingly forever and ever. So any x is available to put in. The range must be negative 4 or higher. What do you think about this guy? This is a cubic. Is there any vertical line that you can draw that will hit this thing in more than one spot? Boy, it makes you wish you could see right in there real close, because I can imagine it's possible that you could have some overlap, but it doesn't look like this one does. I'm going to say yes, this cubic is a function. Its domain is the entire real number set. You can put any x into it. And its range, this will keep growing very slowly, 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 but forever and ever and ever. So both the domain and range on this one are all real numbers from negative infinity to infinity. And finally we come to the square root. Well, it's like this is a parabola tripped on its sides, not really a square root function. But there are many vertical lines that pass through this in more than one spot, so no, that's not a function. All right. This is the end of our lesson today. We'll ask you to try the UTry quiz as quickly as you can, and tomorrow in class we'll be talking about functions, their domains and their ranges, and evaluating them for specific values of the variable. Have a good evening.